Okay, last time I stated this lemma or proposition, I don't know what I called it, of Kazdan and Margulis. Okay, uh, G connected linear semi-simple P group. Then there exists constants C greater than 0, small c greater than 1, and a neighborhood omega of 1 in G with the following properties. I will assume G is contained GLN, and I will write norm for the usual norm and matrices. For any discrete subgroup gamma of G, let me write neighborhoods omega prime, two neighborhoods, one containing the other. For any discrete subgroup gamma of G, there exists G in G with norm G less than or equal to C, and norm of G gamma G inverse minus 1 is greater to C times norm gamma minus 1 for every gamma in gamma intersection omega, while G gamma G inverse is not in omega if gamma is in gamma intersection, if gamma not in gamma intersection omega prime. It is keeps everything outside omega prime, keeps it out, and anything inside omega it pushes out a little bit. Okay. That's why in a finite number of stages you will get out of omega prime. Both these are relatively compact. Relatively compact neighborhoods omega prime. They're small neighborhoods. So if it's if you look at gamma intersection omega, and then you can use this element G to make them get farther away from identity. Here, these are, if it's at a certain distance from identity, this C times C is greater than 1, so it pushes out a little bit. Okay. And it doesn't bring anything inside, anything outside omega prime, it will not bring into omega. It won't bring into omega. So this conjugation step by step keeps elements outside omega prime, but elements in omega it pushes out a little bit. Eventually, in a finite number of stages, you will get out of omega altogether, because omega is a relatively compact set. Ultimately, the distance of anything in omega minus 1, this is going to be bounded. So, in a finite number of steps you will be getting out of it. It is a discrete group, you will have only finite number of elements in the intersection and each one of them keeps going out. That is the lemma or proposition. So, for the proposition, for the proof, we need the following lemma. I use this to prove the two conjectures of Siegel and Selberg. This tells you that eventually, if you take an intersection with a discrete group, eventually the whole thing will move out of this set omega prime. So, omega prime intersection gamma will be trivial. So, if you take any u such that u inverse is contained in omega, then no translative u by gamma will meet u again, because u inverse is contained in omega and omega intersection gamma is empty. If you would have gamma u meets u again, so gamma u will be equal to u prime, which means gamma will be equal to u prime u inverse. So, it will be in u inverse, but u inverse in omega and gamma does not meet, after conjugation this does not meet omega. So, omega u will project bijectively onto the image modulo g gamma g inverse after conjugation, and therefore, that is measure of the quotient will at least measure of omega, measure of u is fixed. For any discrete group I have moved it out of, after conjugation I have moved it out of u inverse. Therefore, you find that there is a lower bound. So, the corollaries I drew last time, corollary 1, so conjecture of Siegel, says that for every semi-simple G, for any semi-simple G, there exists a number mu G such that the Haar measure is greater than or equal to mu G. Mu Haar measure on there is a lower bound set of measure. That is the first corollary. The second corollary we drew was Selberg's conjecture. If Gn in G is a sequence tending to infinity, mod gamma, here gamma a lattice, if G is a sequence tending to infinity mod gamma, then there exists gamma n in gamma such that Gn gamma n Gn inverse. Moreover, the gamma n can be chosen to be the set G where S in gamma is a finite set. Of unipotent elements.
So you are saying for all gamma is not in gamma. This coming back to this Kasdan model is this proposition.
Yeah.
So you are saying that G gamma G inverse is not in omega if gamma is not in gamma intersection omega prime.
Right.
But then there is a space between omega prime and omega.
So, ultimately everything will get out of omega is all I am saying. If it is in omega, it goes up a little bit. If it is not in omega, it stays out of omega. So, only if I am pushing out, every time I am pushing out elements inside omega, but elements outside omega prime are kept out.
Right. Oh, So anyway, it is outside. Everything
Yeah.
is outside. And if it is between omega and omega, can it be
1 second.
inside omega?
Yeah. Suppose it's inside omega, inside here.
Yeah. So can it
Sorry,
be
maybe.
gone back to
No,
omega?
sorry. Then I should be careful. G gamma G inverse is not an omega. Hold on. How should I formulate it? If gamma is an omega, while let me omega prime. I don't know why I put in for. Yeah, there is no need for just omega will do. Sorry, there's a neighborhood omega with this property. So, if it's outside omega, it stays outside, doesn't get in. But if it's inside omega, its distance increases. So, in a finite number of steps, you will get all the elements out of omega. Nothing comes in. See, no new thing comes in at every stage. So that's the lemma. Okay, now, yeah.
Omega can be whatever the convex set.
Sorry.
Omega is a convex neighborhood, or
Omega is it can be convex. It makes no difference. If all that you need is omega is sufficiently small. That's what you need. It can be. I mean, of course, because you are putting in this condition, you can take it to be convex with respect to this norm.
So, also another question,
Yeah.
in your book, you were considering a neighborhood in the D algebra, then projecting down by exponential map, and then considering and taking a norm.
The two things are equivalent.
So
In a neighborhood with identity, whether you take the usual norm distance from the 2 points, you can either define it as g1. You want the norm of g1 minus g2 you can take, or you can take the log
right.
and then take the norm there. The two will be equivalent.
Here the norm is the norm in the GLN.
I am taking norm in GLN.
Mn you are taking norm and just taking it on GLN.
Right. I'm taking norm in GLN.
Doing all that.
See, the point is the exponential map is a diffeomorphism in the neighborhood identity. So whether you put this metric given by the norm, or you take the metric in the tangent space in the Lie algebra and transport it by the exponential map, they are equivalent metrics. So it won't make much of a difference. Okay.
So here the things are much more, simplified in that manner.
Yeah, I'm using this. You will see for obvious reasons. This is the best. You can use the other metric also. Makes no difference. But the problem is that to use other metric, I need the logs of all these elements. I mean, there must be an exponential neighborhood. Of course, there is going to be an exponential neighborhood. We try to take logarithm, but when you push out, the element gets out, and then I do not know if it is in the exponential image or not. So for such reasons, I stick to this. I just take the things in the group, therefore, rather than go to the Lie algebra.
So the entire group has a norm.
Yeah,
Full group has a norm.
GLN has a norm, and therefore a distance metric. Okay, and this says in particular that if G mod gamma is non-compact, then gamma has non-trivial unipotent elements. Because I have a sequence Gn, I say Gn gamma and Gn inverse tends to such that Gn tends to 1, not infinity. There is a sequence. There exists gamma n and gamma set Gn gamma and Gn inverse, but these gamma n can be chosen to be conjugates a finite set of elements. So by passing to a subsequent, I can assume they are all conjugates. Once they are all conjugates, find Gn gamma Gn inverse fixed gamma will go to that. I mean, replacing Gn by Gn times theta n with theta n and gamma, you find Gn theta n, some fixed element S theta n inverse Gn inverse tends to 1. That means the characteristic polynomial of S itself has to be the same as characteristic polynomial 1, which means the element is unipotent. And gamma n is the conjugate of S.
Can you please repeat it?
Yeah, all that I am saying is that this gamma n, you have Gn gamma n Gn inverse going to 1, right? Can assume chosen to be, then gamma n, oh sorry, the gamma n's are all conjugate to fixed finite set of elements. Each gamma n is conjugate to one of a finite set of elements of this kind. Is conjugate to one of the coming from S. That, see, first of all, I have Gn gamma and Gn inverse tends to 1. That comes from what I already proved. The Mahler criterion, the Godma criterion tells you if Gn is a sequence and there is a gamma n such that Gn gamma and Gn inverse goes to 1.
So gamma n can be chosen from a finite.
Gamma n can be chosen as a conjugate of one of the elements in S, conjugate by an element in gamma. Okay, so this means what? Gn gamma n, by passing to a subsequence, I can assume that this is equal to with S and S. This goes to 1. But these are all conjugates. All these are conjugates of a single element S, and it tends the conjugates tend to 1, which means the characteristic polynomial of S is the same as the characteristic polynomial of 1. Therefore, S is unipotent. 1 has all eigenvalues equal to 1. Therefore, S must also have all eigenvalues equal to 1 because the limit it goes to 1. Therefore, S is unipotent. So, gamma n therefore is unipotent. Gamma n is after all the conjugate of S. So, there is a sequence of unipotent. So, in particular that gamma, if G mod gamma is non-compact, gamma contains non-trivial unipotents. Okay. So, if G mod gamma is not compact, then gamma contains non-trivial unipotents. That is Delbecq conjecture. In fact, one can replace this by saying gamma an L subgroup. L subgroup means whenever a sequence goes to infinity, there is a gamma n, G and gamma n.
You wanted to say also not equal to identity.
Huh?
Gamma n in gamma and gamma n not equal to identity.
Yeah. Yeah. Such that G and gamma n. Gamma n L subgroup. The definite L subgroup tells you that is a sequence gamma n, but Karta-Magurs actually show that this sequence gamma n can be chosen inside inside a finite set of conjugacy classes, gamma conjugacy classes, and therefore the elements have to be unipotent. Gamma n for large n will necessarily be unipotent.
How is it shown?
Can
you repeat the argument?
How I showed it? I used this lemma. See, the thing is, you start doing this, and at the last stage, everything goes out of gamma. Okay, everything goes out of omega, and the penultimate stage, since you are conjugating by an element G with norm G less than equal to C, the penultimate stage, the thing will still see, this is omega. At the penultimate stage, it will still avoid a certain neighborhood identity. So, the penultimate stage, what's happened? You are looking at the element G1, G2, GR, gamma intersection omega, sorry, GR gamma intersection omega is going to be empty. This is what you know. And G1, G2, GR gamma intersection a smaller neighborhood omega prime is also going to be empty. GR minus 1, sorry, G2, etc. Just the previous stage, it may not avoid omega, but you are you are applying G1 inverse. When I apply G1 inverse, it can't get to it can't get closer than some omega prime. This is a neighborhood which will still avoid. This means this set G to GR, this product is going to be in a compact set modulo gamma. This avoids the neighborhood identity. It's a L subgroup. So a set of if this G1 G2 GR must stay in a compact set because of this property. It doesn't see, to say that, let me put it like this, gamma is L subgroup if for every neighborhood identity, every relatively compact neighborhood U of 1, the set G in G, G gamma G inverse intersection omega equal to just 1, this set is relatively compact mod gamma. Okay. So that means what? You take G2 etc. GR gamma, intersection omega prime is non-empty, is is equal to, I shouldn't say. This set is going to be relatively compact. So that means the product, the set, I mean this set, the element G2 etc. GR belongs to a relatively compact set. Some fixed relatively compact set it belongs to mod gamma. So this element G2 etc. GR can be written as something in a relatively compact set times gamma, or if you like I can write it as k times gamma with gamma and gamma. And G1, my G1 is also in a bounded set, relatively compact set. So even if I add G1, I am going to get some k prime, sorry, it's a relatively compact set k gamma, so it still will be in a compact set. It's simply G1k, so it stays in a compact set. That so what has happened is G1 G2 GR gamma this means what? G1 G2 GR, let me write G1 G2 GR as some k times gamma with gamma and gamma, and what I do know is there's a last one which gets out, there's a last one which gets out, and that one is in smaller and smaller neighborhood. So the last one to get out, theta gets means what? The last one to get out. Sorry, I forget. No, I'm not writing it correctly. Let me put it down. Sorry. What I should do, the right way to do it is the following. So you have what's happened is this, there is some, so suppose you take a sequence Hn going to infinity mod gamma, then you have Hn, look at this, Hn gamma intersection omega, look at this set. This of course means that there exists gamma n and gamma minus 1 such that Hn gamma Hn inverse tends to 1. This is what we know, because it's an L subgroup. If Hn is a sequence going to infinity mod gamma, I am assuming G mod gamma is non-compact, so there is such a sequence Hn going to infinity mod gamma, and then I know therefore there is a sequence Hn gamma Hn. Now look at, sorry, I should have started like this, look at Hn gamma intersection omega. Now, for large n, this intersection is going to be non-empty, non-trivial. I mean, we have elements other than 1, namely you have some sequence gamma n. Now, on this you start this pushing argument, pushing out and keeping out argument. So you find g g lambda n minus 1, etc. g lambda n, sorry, g1 hn gamma intersection omega reduces to 1. Okay. This means this product g lambda etc. is going to be relatively compact modulo gamma. This product g lambda n, g lambda n minus 1, etc. g1 hn, this is in fixed relatively compact set which depends on omega.
So you are doing it for every n.
Yeah, for every n I look at this stuff.
So every n you are getting such a sequence. So g1,
Yeah,
g lambda.
I fix an n, then you find a sequence like this. Keep pushing out till you are got rid of everything outside omega. You have done that. So this is, and then once it's outside omega, the set of elements which have this property is set of alpha such that alpha gamma intersection omega equals just 1 is relatively compact modulo gamma, which means I can find this element is in k lambda gamma for k omega, where k is some compact set.
Yeah, but that compact set might depend on hn also.
Depends only on omega. Set of elements which keep everything outside omega, other than identity keeps outside omega, is a relatively compact set. For a fixed omega, it depends only on omega, nothing to do with my n. So this has got into k omega gamma. On the other hand, if you look at g lambda n minus 1, etc., yeah, look at the last one. You know, when you keep pushing out, elements keep expanding in norm. No, there is one which gets out last. There's one which gets out last. The last one to get out, let theta n be the last one, last element of gamma hn gamma intersection omega to get out of omega. Okay. How do I? Hold on.
Also, I have is this in Kasdan-Margulis theorem? Is this omega G invariant conjugation under G?
No.
That's
Oh, if you, I said omega. In fact, omega is relatively, I want a relatively compact neighborhood. You conjugate by G.
But then if you conjugate, it stays in a different. So you get a.
There is a suitable G.
Every time you conjugate by G.
There is a suitable G. You make one conjugation, there will still be some elements inside omega, then you may need a different G. I am not saying the same G is going to work. The only condition on G is that G stays within a bounded set, in a relatively compact set. Okay, so what happens? Yeah, let me put it like this. This is in k omega. Yeah. Now that really means hold on. This is in k omega. I pushed Hn, then dragged it out one by one. Theta n be the last element gamma intersection. Sorry, yeah, Hn gamma intersection omega. The last element to get out. Yeah. Okay. So G lambda n minus 1 etc. G1 Hn is some un gamma n kn gamma n with kn yeah with kn gamma n with kn in k omega. Okay. Now kn k omega I'm getting a bit confused. Times Hn is in kn gamma n, kn in a compact set. Okay, and now yeah, and we also know that g lambda n minus 1 G1 Hn of the okay, I'm getting lost. So I don't know what's happening here. Is equal to kn gamma n with kn in k omega. This avoids omega. Yeah, and what do I know? I also know that this is true. G lambda n minus 1 etc. lambda n minus 2 etc. G1 Hn gamma yeah okay. So in fact this implies that G lambda n minus 1 G1 G lambda n minus 2 etc. G1 Hn is in some kn prime. This G lambda n is in a bounded set. Every time I am expanding, so some other kn prime gamma n with kn prime in some compact set, kn prime in k omega prime, maybe slightly bigger compact set, I do not care. Okay. Now let us see what happens to G1 Hn. Yeah, let theta n be the last element of Hn gamma intersection omega to get out of omega. Under the sequence of operations, each time some element gets out. So when I look at this much, theta n doesn't get out, okay. But if when I apply one more, it has gotten out, G lambda n, one more, it's gotten out. That is the situation. Now let's see what happens to
Getting out means after conjugating by.
yeah. Each time I am applying this conjugation, after one more conjugation it gets out. Till that stage it doesn't get out. So I now look at G lambda n minus 1, G lambda n minus 2, etc. G1 Hn theta n look at this times theta n. Hold on, I am really getting confused. See, the last one to get out, this is in some compact set, it is in Kn prime omega prime, and look at this is equal to Kn prime gamma, I wrote it as Kn prime gamma n times theta n, okay, and this is in Kn prime gamma prime theta n I'm really confused. What do I, the last one to get out is theta n, this is still in some omega 1 contained omega naught, this is in omega 1, that means this is this element, I have written this element as Kn gamma n theta n gamma n inverse Kn prime inverse omega n, which implies gamma n theta n gamma n inverse is in Kn prime inverse omega 1 Kn prime inverse Kn prime. Is that clear? See, this whole thing after conjugation gets into omega 1, but this element whole thing has been written as Kn prime gamma n. So Kn prime gamma n conjugate theta n by Kn prime gamma n, theta n was the last one to get out, that last one was still in omega 1, which is maybe a smaller open set, but some neighborhood of identity, okay. That means, but gamma n theta n gamma inverse gets into this set, this is compact, and this is in gamma. So it's a finite set, this set I call S, okay, and the last one to get out therefore is conjugate to the so the last one to get out is conjugate to some element of S, and the last one to get out under Hn, it must be very small, because when I multiply by, there are lambda n elements here, after each time it goes up only by C. So it will go up by C power lambda n. Okay. C power lambda n, every element goes at least by C power lambda n, but therefore if the original thing was within epsilon, then it would have gone to C power lambda n times epsilon. Okay. So everything has got out by then, and the last one, the one which comes out last, therefore is 1 over C power, C power lambda n is some number, it will become epsilon by C power lambda n. That's where it will be. I mean, it's got out beyond omega, so some constant, the beyond omega the norm will always be greater than some constant b. Go b power lambda n, it will become like b power C power lambda n. The last one to get out will have at least norm at most this, therefore it goes to 0. The last, so the one which goes to, you have the sequence theta n which is dragged to 0 by our original sequence Hn, and all the theta n are conjugates to one of a finite set of elements under gamma. So that's how you prove that the element has to be unipotent. All conjugates tend to 1, conjugates under gamma, but conjugates under gamma, therefore the characteristic polynomial tends to 1. But these are the same characteristic polynomial tends to 1, but it is the same characteristic polynomial because they are all conjugates, and therefore it must be the characteristic polynomial of 1. That's the only way out, which means the element is unipotent. Okay, sorry, it's didn't explain it too well, but it's you done in my book. See that. Go back and refer to it. So that proves the Selbach conjecture and how do you prove this statement that you can push out and keep out in the way I've said here. The idea is this: it depends on a lemma which is actually due to Zassenhaus, essentially due to Zassenhaus. Says the following: G be any Lie group, then there exists a neighborhood omega of 1 in G such that if gamma is any discrete group, any discrete subgroup of G, then gamma intersection omega is contained in a connected nilpotent Lie subgroup. Say n of G. Take a discrete group, intersect with this neighborhood, then the group generated by that in particular is nilpotent and is contained in the connected nilpotent Lie group. That is the statement. Okay. The proof goes like this. Firstly, observe that see, you can assume without loss of generality is G is JLN, because any group is locally isomorphically linear group, embedded in linear group, and you are only talking about neighborhood of the identity, and therefore I can assume you are working with JLN in matrices. Can assume now you have the following thing. Look at elements. If G equals for G H in G, I'll write.
Why can you assume GLN?
The whole thing is we are talking about a neighborhood identity. G is locally isomorphic to a linear group. You can give a homomorphism of G which is an isomorphism near the identity. 1 1 which is near the identity. The image, you can take the image subgroup of GLN. Okay, and inside GLN, if the neighborhood is sufficiently small, we know that the exponential map of a neighborhood 0 maps isomorphically onto that. What is the I'm taking a connected, how am I going to get a connected nilpotent group? It's going to be those, I just take the elements gamma and take the logarithms. If the neighborhood is sufficiently small, I can take the logarithms, and then I take the Lie algebra spanned by that. That has got to be nilpotent. If the group generated by this gamma is going to be nilpotent, it's going to be, we will see the proof tells you that the Lie algebra will be nilpotent. So that's why it works. You just have to take the image and do it in GLN, and the exponential neighborhood I've chosen is so small that
we can just work with that joint representation.
You can't use that joint representation because the joint, there's center coming up. In some sense, you can in some sense, because modulo the center, if it's nilpotent, you can it's okay. The group is nilpotent. You can also do it that way. But I'll tell you why I'm saying GLN. A joint also, then you're still landing in GLN in any case.
So
Except
using that, can you
no, except there's a small question whether the image of the adjoint group may not be closed. Okay, if the image of the adjoint group is not closed, then I can't use the exponential neighborhood properly. So, but you can always find a quotient of G which linearly embeds as a closed subgroup in GLN. From Adolph's theorem, we can do that. So that's why you can assume G. Otherwise, what I want to say is, if there is no loss of generalization, assume G to be a closed subgroup of GLN, and then you can take over to GLN. And see, the point is that also the image of a discrete group under the adjoint may not be discrete. Even if image is close, image of gamma may not be discrete. So I'll have to make sure that the image is discrete, for which I'll have to do something like this. Okay, but you can see the proof. You can modify it so that you don't have to go to GLN. You'll see that. The way I'm going to use it is the following. You look at, so G in GH, by definition will be GH, G inverse, H inverse. The commutator, by bracket GH. So write G as 1 plus X, H is 1 plus Y. I am assuming, so norm X, suppose norm X is less than epsilon, norm Y is also less than epsilon. What can I say about the commutator? I write the commutator GH as 1 plus Z, and I want to estimate Z in terms of the estimates on X and Y. You're going to see it will look like epsilon square. That's what I want to say. How do I say that? You find that G is 1 plus X and H is 1 plus Y. Yeah, let me write G at G inverse in the following form. G at G inverse, H inverse will be G is 1 plus X into 1 plus, let me write G at G inverse, let me write like minus 1. This is what going to be, Z is going to be this. I write this as GH, I keep out, and then I can write this as G inverse one second, what's the right way to do it? G as G inverse minus 1, I write it as G times H into G inverse H inverse minus H inverse G inverse. Okay. That's equal to GH, I'll keep it as such. G inverse H inverse G inverse. If I write G inverse, maybe I'll keep it the other way around. Let me write, sorry, I'll write this as GH minus HG into G inverse H inverse. Write Z like this. This is going to be equal to GH minus HG, but that's same thing as XY minus YX. Commutator, because I'm only adding a scalar matrix, the commutator, the bracket of H and G is same as bracket of X and Y, and what I have here is a bracket GH minus HG. So times G inverse H inverse. Okay. And therefore, if I look at norm Z is less than or equal to norm X, norm Y, xy minus yx, I can, it's norm x norm y plus norm x norm y norm x, which I read to norm xy, times C, where C is 1 plus epsilon, C is, yeah, 1 minus epsilon inverse. I mean, what I mean is G, okay, G is 1 plus x, so G inverse is 1 minus x plus x square, etc. And then you can estimate this as norm of G inverse will be less than or equal to 1 minus epsilon inverse from this estimate. And similarly for the other one, so you find some constant C. So if the 1 minus epsilon is less than epsilon, so inverse will be less than greater than 1. So this is the right one. No, I'm just writing here 1 minus epsilon plus epsilon square. I can know I have to replace it by 1. See, when I write G inverse, the inverse is what I want to write. So I'll have to replace by 1 plus norm x plus norm x square, etc. If I want to estimate a norm G inverse, I'll have to put plus everywhere and norm everywhere, which is 1 minus epsilon inverse. Norm x is less than or equal to epsilon, so 1 minus epsilon inverse. Okay. So this if I fix epsilon, this C will depend on epsilon anyway. C epsilon. Sorry. Yeah, G at G inverse, I write it as, look at what I have written here, minus 1 is what G at G inverse H inverse minus 1 is GH minus HG into G inverse H inverse GH, that is the first term, and this is 1. So that is why I have written it like this, which is same as xy minus yx, because 1 commutes with everything, 1 plus G, so same as xy minus yx. So for xy minus yx, I know it is less than or equal to 2 norm. So norm Z therefore becomes less than or equal to twice norm xy times C epsilon, which is less than or equal to epsilon square times C epsilon. Anyway, the point is I get norm Z, which is norm of the commutator GH minus 1. Let me put it like norm of GH minus 1 is less than or equal to norm x norm y into some constant C. If the neighborhood is sufficiently small, I can fix a C and I will get such an inequality. Okay. Now I keep taking, fix one of the elements G and keep taking commutator of that with, take bracket GH, then G bracket GH, etc., like in the descending center series. Then what happens? Then you take the commutators, the thing will become, so if I take the commutator, repeated commutator, less than or equal to norm x I can actually assume that
But this is under the assumption that x is.
1 minute. Sorry.
So when you are taking x is inside, norm of x is less than epsilon. But then if you take the commutator, is it can it go?
No, that when I take commutator, see, if I fix y, it will still be epsilon times something.
So that is less than epsilon.
This is I can fix some m, it will be less than m times epsilon. So what happened is you find that this is less than or equal to norm x power. I keep repeating. I'm going to get norm x power. These are n times power n, then norm y, then c power c epsilon power n. No, I don't have to. Sorry. Yeah. No, I just want to write. The first commutator I get this kind of thing, and the next commutator c epsilon power n. So I seem to get c epsilon power. There's something not quite okay.
C
One moment.
You don't get power in C.
No, 1 second. 1 second. No, let me put it like this. I'm going to take. Yeah. Right. I'm going to take something like this. The set. Yeah. I want norm G. Yeah. Look at the set of. Yeah. 1 second. I'm going to assume that omega will be the set G, norm G less than or equal to norm G inverse less than 1 and G minus 1 norm less than epsilon, where epsilon less than half, say. I'm going to do it like this. I'll take this to be the set omega, set of points where G is norm G inverse is less. Oh, I'm sorry, no, I can't say that because it's 1 plus something, right? No, I can't. Yeah, norm G inverse less than, okay. Let me put norm G less than or equal to, say 1 plus something, okay, 3 by 2. One-fourth. Let me take it like this. Epsilon is less than to 1/4, and I want norm G minus 1 to be less than epsilon, while G inverse is less than 3 by 2. If I do that, what do I get here? So G inverse already I made it 3 by 2. If I do that here, now this I'm going to get twice norm x, norm y times 3 by 2. 3 times this is what I'm going to. Norm z is going to less than norm x, norm y 3 times that. Repeat this. Take one more commutator with this, for instance. So if I look at the commutator 1 plus z, 1 plus x, the commutator, I'm going to get less than or equal to norm x. I have to replace y by z, so I have to replace norm z so I'm going to get something like that, right?
Why?
Norm x, no, I'm looking at now 1 plus x 1 plus z the commutator. So here y has to be replaced by z, norm y therefore becomes norm z, and there is 3 still there, norm x, norm z 3, which is in turn this is equal to norm x square, sorry, no, I have to replace by, yeah, norm y has to be replaced by norm z, which will give you norm x square, norm y 3 square. Okay, norm x, so norm x square norm y into 3 square. Okay, now look at norm x square, and then if I see, my assumption is that norm G inverse is that, whereas omega is a set of points, G minus 1 is less than epsilon. So norm y is also, this is also less than 1/4 square, this is less than 1/4. Keep repeating. So what I want to say is the following: if I look at this, I'm going to get norm x power n times norm y times 3 power by induction. I'm going to get,
You are saying that if I take my elements to be very small, to very close to identity, their commutators
shrink very fast.
shrink very fast.
See, one of them, fix one of them, the other is small. The first commutator already it will be epsilon times that. Next one is epsilon square. Some constant, of course, will come up. That's epsilon cubed and so on. It shrinks. So this, if I repeat this, so this tends to 0 as n tends to infinity, because norm x power n produces 1/4 power n, and you will therefore get 3/4 power n, so it goes to 0. Now, but these elements, if they are in the discrete group, if G and H are the discrete group, clearly if it shrinks to 0, ultimately it has to be 1. So if I take the set of elements in this group and form all kinds of commutators with come in the descending center series, they tend to they become ultimately 1. Okay, in a finite number of steps they become 1, depends on the minimal value of gamma. So okay, in finite number of steps it has become 1, but that means the group is not, suppose a group is generated by set of elements here, yes, finite set of elements, such that you form the descending center series only coming from those elements, that ultimately is, so if those elements become 1 after in a finite stage, the group is nilpotent.
The group generated by that
That is nilpotent, because you can take the last ones which will be central, pass to the quotient, and so on. So it becomes nilpotent, and you want to say that actually the connected nilpotent group, you take the logarithms of these, so then take the Lie algebra elements and take brackets. Okay, see, x is essentially Lie algebra element, logarithm will become x plus etc etc, and again take the Lie algebra brackets and things of that kind, you find there again the central series is going to be 0, so the Lie algebra is nilpotent. Or another way of looking at it is, you can take this, I'm sitting inside JLN, you can take this Discrete closure. Discrete closure of nilpotent group will be a nilpotent group. Nilpotent group. It has only, because an algebraic group it has only finitely many connected components, so you can take the identity connected component, and the identity connected component will have to contain all these elements.
But then you take
If omega is small, all these elements will have to be contained in the identity connected component. So you got a nilpotent Lie group, connected nilpotent Lie group containing all these elements, which is what I want. Zasnow's lemma says gamma guys contain the connected nilpotent Lie group n of G. Okay. Now how am I going to use this?
So you are saying that so gamma intersection omega, if I take the commutators, then I take the group generated by that, take the Discrete closure, that is a nilpotent.
That's a nilpotent group.
Now it might be a disconnected
Yeah, so I take the identity connected component.
Okay, then
Then points sufficiently near the identity will be captured.
so then do I have to take a smaller neighborhood which is
Not really, not really. The point is, you see,
connected?
how do I say that? The point is, you take the, in an nilpotent Lie group, the exponential map is well behaved. So you don't have to you just have to think a little bit. It's I'm sorry, I'm not explaining too well, but you just take the connected component, it works. But in any case, you can also start arguing with the Lie algebra elements. You take brackets and the Lie algebra elements. You can do the same thing which I have done, and you have to show, of course, that they go to identity. I mean, for sufficiently small, they become 0 is what you have to show, and that is because well, it requires a little bit of work. But the other argument will work in nilpotent Lie algebra, because in a nilpotent Lie algebra, you simply connect a nilpotent Lie group exponential map with an isomorphism. You can use that. The group may not be simply connected, but still you will be able to use that kind of argument. I don't want to spend more time on this. I already have messed it up a little bit. So the Zastro's lemma tells this happens. Then now what happens is this: you fix this, you choose this omega to be this kind of neighborhood, Zastro's neighborhood. Okay. Then all the elements you want to push out are going to be contained in a fixed nilpotent group, because the group generated by them is contained in a fixed connected nilpotent group.
My omega is going to be the Jason's
Jason's neighborhood. So, and so it's going to be contained in nilpotent group. Nilpotent group means what? It's going to be contained in, if we are working in GLN, which you can, as a matter of fact, from what you see here. If you're working in GLN, you have the Iwasawa decomposition KAN, and everything has to lie in A times n. If it's nilpotent, it has to lie in, it is soluble, therefore it has to lie in A times n. Okay. You have the Iwasawa decomposition.
But there can be abelian,
Huh? Now my group is nilpotent connected. So I can take, for instance, I take n, take bracket nn. Well, the thing is, it's going to be contained, anything soluble is going to be contained in A is diagonals. So it's going to be, in the case of GLN, it's going to be, this is all diagonals. Any soluble group is going to be contained in that, and therefore any nilpotent group is going to be contained in this. So I have to start with a nilpotent group contained in this and try to push it out.
but it can it can be in a maximal torus of the maximal compact, right?
No, it can't be, because it kind of normalizes a nilpotent group. You see, you have this group n which is nilpotent. Well, all right, in principle it can be, but okay, how do I say that? Well, let me slur over it. Suppose it's going to be in this, okay, then all the elements of n can be expanded, okay, and in D you cannot expand. You can expand with the elements of n by applying conjugation by elements of n. You can expand elements in D, or you can take n minus, one of these, either n minus or n, one of them you can use to expand that. So first expand it by, these are positive, you take something like this, A1, A2, An with A1 greater than A2, A2 greater than A3, etc. You take such an element and can use that to expand anything in n. It may not expand things in D, but things in D can be expanded by some element in n or n minus, one of those things. Okay. So what you do is you apply sufficiently high power of diagonal element to expand the things coming. Those you can write every element as having a component here and a component here. This component can be expanded by some power of A. Okay, some power of an element in this. This component can be expanded by some element by conjugation.
Only when, by conjugation.
By conjugation by an element here, because if you look at the element here, it starts, so it's exponential of t, say x, say it will start off with x plus y plus, sorry, x plus bracket xy. When I apply conjugation, add yx. We'll get an expansion like that.
So that's you're talking about elements of n.
I'm using y in n, the Lie algebra.
Oh, x is in
When I expand like this, so x plus it picks up tail. So it, and this, the norm, it's orthogonal. The things are orthogonal. The norm will increase. Okay. For elements, so every element is a component here and a component here. If the component here is the bigger component, you can use a to expand it. Element in the diagonal to expand it. If the component here is bigger, use something here to expand it. So you have to combine the two things, and then you can find, you can expand everything inside. Inside dn, you can expand everything. That's the kind of thing that happens. But you know, anything is conjugate to, any nilpotent group is going to be conjugate to one of these. As I say, it may not be dn, it will be n times some nilpotent groups times something which centralizes it, some semi-simple part which centralizes it. Okay. So it's a, and now you can start with the n and take its normalizer. It will contain the other part already. Take the unipotent radical, again take normalizer, etc., etc. You will end up in some parabolic group. Okay. And every time you take normalizer, this the semi-simple part will be present. It won't change because you start with u, normalizer of u, and then you take the unipotent radical. Notice that the group which normalizes u will also normalize, it's contained in nu, it will also normalize, and you take this procedure, complete this procedure, will end up in a parabolic group, and that parabolic group will contain your nilpotent group. Okay, and therefore the group will be not quite, it may not be upper triangular, it could be blocks like this. This again you can expand in the same way. There is some part which will come here, and some part will come here. So nilpotent, so group, whole group is nilpotent. So it will be some part coming here, product that. These you expand by using elements here, and this you expand by using diagonal elements. So since everything is conjugate to a finite number of such possibilities, you can you know, it's enough under everything under the compact group. So it's enough to do for one of them. You have to do it only for a finite number of them, which you can. So to do it for a finite number, you just have to do it for one of them, that you can find an element g with norm g less than equal to c. Some g, a priori you don't impose the condition norm g, but then there are only finitely many. You get g1, g2, gr, and their sup norm will do the job for you, because everything is conjugate under the compact group, so which preserves the norm. So that's the proof. Sorry, I have not done it too well.
Jasanoff's neighborhood is going to work.
Jasanoff's lemma is the main thing.
The neighborhood is also going to work.
Huh?
The neighborhood in Jasanoff's lemma is also going to work.
Which?
This neighborhood of Jasanoff's lemma.
Yeah, that's what's going to work, right? That's, yeah, neighborhood of Jasanoff's lemma is what's going to work. The point is, for one nilpotent, connected nilpotently group, you have a g, which you fix one nilpotently group, you have a g which does the expansion, and then you are only interested in, there are only one nilpotent, any nilpotent group is contained in some parabolic group, well chosen parabolic group. In the parabolic group, the nilpotent group breaks up into, if it's Zariski closed, it's going to break up into something in the diagonal part and something in the unipotent radical, and for each such thing you can do it, and therefore, and there are only finite up to conjugacy by k, which preserves a norm. You have only finitely many elements, you have to choose only finitely many elements for these things, and corresponding conjugates for the others. That does the job. So, if the connected nilpotent group is contained in some parabolic group such that it is a product of something in the diagonal blocks times something in the unipotent radical, then I can find it's some g with norm g less than c for that's kind of thing that you have to do. I mean, in general, you have to talk of if a semi-simple group, you have to take parabolic groups which also have the same behavior. I mean,
Was this the original argument of
sorry,
Is this the original?
this is the argument. This is the argument. It's again, it's in my book. The same argument is reproduced in my book. Okay, I think we should get our coffee. Okay, now let me restate. From this corollary, we have the following: if gamma in G semi-simple is an L subgroup, there exists a finite subset with G mod gamma non-compact. There exists, it should also, I have to be a little careful. I didn't quite state this. G semi-simple has no compact factors. I'll tell you why this is needed. G mod gamma with G mod gamma non-compact, then there exists a finite set S of unipotent elements in gamma minus 1 such that for every sequence Gn in G which tends to infinity mod gamma there is a subsequence there is a sequence gamma n in gamma and Sn in S. Of course, this means S is finite. When I say S in sequence, it will keep repeating after finite number of terms anyway. And Sn in S such that Gn gamma n Sn gamma n inverse gamma n inverse Gn inverse tends to 1 as n tends to infinity. This is what we have proved as a corollary of this. Yes, this is set of unipotent elements. That is the it's a sharper statement than the mere statement there exists unipotence, etc., which is due to Selberg. Now, from this, we'll deduce the following. Yeah, I said has no compact factors. This has to be assumed for the following reason. See, if you have G cross a compact group, and the gamma in G is a lattice or an L subgroup. A lattice is an L subgroup, as we know, and then you can suppose F gamma to K is any homomorphism. Then we have look at set of elements gamma, comma f gamma, gamma in gamma. This becomes a lattice in G cross K. Because K is compact, G mod gamma, if it's an L subgroup in G, then this becomes an L subgroup. And now, even if gamma is unipotent, F gamma, if it's non-trivial, is not going to be unipotent. And the pair is not going to therefore to be unipotent. So in a trivial way, it will fail. So to avoid that, you have to assume that there's no compact factors. If you look at the proof, you'll have to be, you pointed out that something can come from K. Ultimately, that doesn't happen, basically. It's essentially everything is going to be in An if it's gamma is non-co-compact and so on. If G has no compact factors, the K thing will come in only if there are compact factors. That's the kind of thing that happens. Anyway, so this is the okay. One consequence of this corollary, a corollary to the corollary, if you like, is the following. G semi-simple and defined over Q simple. It is, it has no algebraic, normal algebraic subgroup defined over Q. Then G has only finitely many conjugate classes. Of unipotent, of maximal unipotent Q subgroups. Finitely many gamma conjugate classes. Gamma is an arithmetic subgroup.
So I'm just about this example. This gamma f gamma, you are saying that's going to be lattice in G cross K.
Start with
The lattice
and then look at the diagonals of embedding of gamma. That's again going to be a lattice because K is compact. G cross K modulo gamma. You can pass the quotient by K to decide whether it's a lattice or not.
You are saying image of gamma is going to be also discrete in K?
Modulo compact group. Projection is proper. G cross K.
Oh, this diagonal.
The diagonal thing will project onto a discrete subgroup in G. It will project to gamma in G. If you project modulo K, it's going to project to gamma in G.
Okay.
So it's not a problem. So now the corollary says that if you have a simple group defined over Q and Q simple and gamma arithmetic, then G has only finitely many conjugacy classes of unipotent K subgroups, unipotent Q subgroups. Now, the moment G has a unipotent Q subgroup, there will be a diagonal torus which will be dragging elements in integral elements in the unipotent group to identity. Like the upper triangle, you take the upper triangular matrices, you have the upper triangular unipotents, and you take a suitable diagonal element, conjugation by the diagonal element, any element in the unipotent group in the upper triangular unipotent is dragged to the identity element. In particular, integral elements will drag to the identity element. So the quotient therefore is going to be non-compact. The quotient cannot be compact. That is the Guzman criterion. And then it's also a fact that if it's Q simple and has a non-trivial unipotent subgroup, suppose it has a non-trivial unipotent subgroup and it's a Q simple, then when you take real points, it cannot have compact factors. Because if you take the Q points, project any Q point to the compact factor, you will get a semi-simple element. And GQ sits diagonally. No element of GQ can project to a trivial element in any factor, in a real factor. So it has no. It's automatic that it has no. GR has no compact factors. Now, we start with U in GR be a unipotent subgroup. Then there exists, this comes from the structure theory, which I have not gone into in great detail. I have not really gone into structure theory, but anyway, the following thing is true. Then there exists an element A in GR diagonalizing, normalizing U such that A power n G A power minus n tends to 1 for every G in unipotent group over Q. It drags everything in UR to identity. This is like the upper U is the prototype is look at G equal to GLN, and the upper triangular unipotence is U, and diagonal is the same. And then if you take any diagonal matrix with A1 greater than A2 etc. AN, the product equal to 1, then you can see that it will drag every element in, like the upper triangular element TT inverse in SL2 drags any element here. In you conjugate, it gets multiplied with T square. So if T is less than 1, it will drag to 0. It will drag the whole thing to identity element, conjugation by that. So it becomes.
In that statement, you are using gamma i.
Sorry?
So I am not getting gamma i. Gamma i.
Gamma?
Yeah. Gamma is the G is Q simple. You are assuming G is in the corollary statement. You are assuming G to be Q simple.
U being Q simple doesn't make sense. U is unipotent group.
No, G.
G I am assuming is Q simple. See, I think the product of it will decompose the product, and the corresponding arithmetic group will also decompose the product. So it's you have to need only consider that case. I mean, in general also it's true, but once you do it for this Q simple case, it follows for the general case because everything is a product of Q simple things. Okay, there is an element A like this for every U. Maybe I'll call it AU, depending on U. This happens for every G. In particular, for elements, integral elements, they will be dragged to the identity, which shows, in particular, the quotient is not compact. Quotient by an arithmetic group is not compact because G can be taken in UZ minus 1 in particular. If U is non-trivial, this group is non-trivial, so there will be elements there which can be dragged to the identity. Okay, now what happens is this. Look at this. So AU power n, sorry, A power n U, so AU power n drags, yeah, we know that this goes to 1, therefore it follows that there exists gamma n in gamma such that A power n U gamma n a power minus n u tends to 1, and gamma n itself is of the form some rho n Sn rho n inverse with Sn in the finite set S in gamma. That's what the corollary said. There is a finite set S which this happens. Passing to a subsequence, and let's look at another. Yeah, suppose u prime is another unipotent group, another maximal unipotent. Then I know that au power n, au prime power n g au prime power minus n tends to 1, and again there is a n au prime power n gamma prime n, which will be rho n prime Sn prime rho n inverse n au prime power n Sn tends to 1. Now, this means for large n, this conjugation will land this in a Zastanov neighborhood. This conjugation will land it in a Zastanov neighborhood. And it's also true for, let us fix generators, finite number of generators. Say alpha 1 etc. alpha n, alpha r for uz, and u intercept in gamma. Make now look at AU1 prime, AU1 times gamma n. This will drag the gamma n inverse alpha I is in Zastanov's neighborhood for n greater than 0. And similarly, A prime, AU and prime, not UN, AU prime power n. I called it should have said here for, yeah, I had gamma n actually was AU1 gamma n inverse alpha I, right? And similarly, AU1 prime gamma n prime of gamma n inverse beta j. Now, all this, we also have the first one, A and U, gamma n, which also drags gamma n rho n. Sorry, I'm getting here. It's gamma n, I wrote the, yeah. that gamma n is bad notation, sorry. What I mean is that AUN, this gamma n inverse alpha I, yeah, gamma n is right, sorry. Gamma n inverse, no, A and U drags, what I mean is, A and gamma n, A and U gamma n inverse conjugates alpha I, because gamma n inverse 1. So this element conjugates to identity, this element conjugates this to the towards identity. Both these elements going to, therefore they are going to Zarsky neighborhood for large n. And you also have A and U rho n Sn rho n inverse A and U inverse tending to, again in Zastrown's neighborhood. Let me call this Zastrown's neighborhood some omega for large n. Passing to a subsequence, I can actually say, take the Sn to be the same here, and similarly here A n U rho n prime Sn prime rho n inverse prime inverse A n minus 1 U prime is an omega. This really means A n U gamma n sulphi is in the Zastrown's neighborhood. What I can do is the following. I can look at this element along with see, I can introduce, how do I say this? What I want to say is the following. Okay, I introduce artificially a gamma n inverse here. Then I find that gamma n inverse Sn rho n inverse gamma n, this and this bunch here are both conjugated by the same element A and U gamma n into a Zastrown's neighborhood. That means a conjugate of this element Sn by an element of gamma falls into the Zastrown's neighborhood together with these elements after conjugation, but then together they generate a unipotent group. They are all unipotent elements. They generate a unipotent group together because of, they generate a unipotent group, therefore unipotent group by the lemma, Zastrown's lemma. Okay. So after conjugation, this gamma n, this Sn really falls into U. That's what it amounts to. After this conjugation, it falls into this conjugate, but this is conjugate to, the group generator is conjugate to U, and U is maximal unipotent, so this element must fall into U. So this, now there are only finitely many such conjugates. From this, it's not difficult to see that the number of conjugates, maximal unipotent groups are conjugate is also finite. It requires a little bit more of work, but I won't. I'm not going into it now. You can use some kind of induction and arrive at that. Okay. So there are only finitely many conjugacy classes, gamma conjugacy classes of maximal unipotent groups. Huh? Maximal unipotent Q groups, yeah.
Also, this GR has no compact factor. I didn't get that.
No, see, the point is, if you look at G, suppose it's Q simple, but it may not be simple over R. Over R, it breaks up into product some GI. And then you have GQ here. GQ has a diagonal embedding in product of GIR. What I am doing is Q is contained in R. So GQ gets into GR, but GR is product of GIR. but the various factors here, the mapping of GQ embeds diagonally. In every projection, the mapping is an injection. See, you are looking at the real way of saying it is, when I say arithmetic group, I've started the number field K. Okay. And then I'm going to look at K tensor R over Q. The general arithmetic group by definition is a subgroup of integral points in some number field. That's the way it was defined. So you have GK to GK tensor R. Inside here you have GO. That goes into a discrete group here. This is GR. When I treat G as the algebraic group over Q, this is going to be GR. GK tensor R over Q is GR. So, and GK sits diagonally here. GO is same thing as, let me put it like this: G over K, and now G prime will be that group being treated as a group over Q. Or if you like, let me write this way, the other way around, G prime. I started, so G prime K tensor R, that's same as GQ. And GQ, GO is same as, sorry, this is G prime O, which is same as GQ. G prime O sits diagonally here. And in each factor, it will be an injection. K embeds in different components of K. K tensor R breaks up into a number of fields, some R, some C. And each embedding of K in that component will give you an injection of GK into that part, which means correspondingly you get a mapping of GQ, which is diagonal. So in every simple component it projects injectively. Okay. So if there's a compact factor, it will project injectively there. But in the compact factor, every element is semi-simple. So elements of GQ will become semi-simple. Our assumption is that G is so then it can have no unipotent elements. So I am interested in the case when G has unipotent elements. So the statement I am making is it has only finitely many gamma conjugacy class of maximum unipotents. If the maximum unipotents are trivial, there is nothing to prove. Then the group is, then G mod gamma is compact. And there are going to be no unipotent elements there. So when there are unipotent elements, that really means there are no compact factors. If there is a compact factor, every element of gamma becomes semi-simple, every element GQ becomes semi-simple. Being semi-simple is something which you can verify in one embedding of the number field. If in one embedding the number it goes into a compact group, then obviously the elements are semi-simple there.
So Q simplicity is important.
Q simple is important, yes, and really Q simple, Q isotropic. That's the case one is looking at, because if it's not if it's anisotropic, there are no maximum unipotent subgroups. There's nothing to prove, and this is the statement. Okay, so what was I saying? So and then, so once you have the fact there are only finitely many conjugacy classes, then from that one can deduce, but I am not going to do that. I refer you to Borel's book on arithmetic groups. Theorem Borel. GB in algebraic group defined over Q. Let T be a maximal K-split torus xt the character group of T. then xt one is knows is isomorphic to Z, and introduce an order on xt, that is, see, an element, fix a basis of xt, and say an element, say fix a basis E1, E2, EL t, and alpha in xt equals sigma alpha I ei I equal to 1 to L is greater than 0 if the first non-vanishing alpha is greater than 0. See, this is the base xt is ZL, xt is corresponding to free abelian group on L.
G is an algebraic group defined over K, is it?
I'm saying, T be a maximal Q split torus. Then if the first what it is, non-vanishing alpha is greater than 0. It's called lexicographic ordering. Okay. The first non-vanishing coefficient alpha ordered 1, 2, 3 L. So maybe fix a ordered basis. Then if I look at the Lie algebra, LG breaks up into eigenspaces. LG over Q breaks up into eigenspaces for T. Any torus acting on a vector space, so a split torus over Q acting on a vector space, if the action is defined over Q, acting linearly, breaks up into eigenspaces. So let me also write G here. G equal to sigma, let me write ZT plus sigma G phi greater than 0, direct sum sigma G minus phi greater than 0. These are eigenspaces. Corresponding to phi this to minus phi. Everything breaks up like this. Under the Lie algebra, this ZT is centralizer of T, that is zero eigenspace or trivial eigenspace, not zero, centralizer of T. Lie algebra breaks up this, and this part, which I call U, is a nilpotent Lie algebra. The corresponding group is denoted U plus. Nilpotent Lie algebra, let me call that small u plus, and this one is similarly U minus and U minus. Let me denote by, for T greater than 0, let U plus, let A sub T be the set of elements. ZT itself I must also say here. ZT decomposes as M plus T where T is the Lie algebra of T and M is the subalgebra defined over Q and M and T are orthogonal with respect to the Killing form. On the Lie algebra, there is the Killing form which is non-degenerate, is orthogonal. Moreover, and the Lie subgroup corresponding to MR real points of MR, Lie subgroup M corresponding to MR is compact. All these are facts which have to. Now the statement goes like this. We know that let psi in GQ, sorry, in yeah, well, okay. Let UI I in S be a fine set of unipotent Q sub maximal unipotent K subgroups. Oh yeah, I must say here. Let me before I say that. The group U which you get here, the subgroup of G, the algebraic subgroup of G, is automatically corresponding to U plus minus R maximal unipotent Q subgroups of G. Every maximal unipotent Q subgroup is conjugate to U plus under some element of GQ. GQ acts transitively on the set of all maximal unipotent subgroups. Okay. Now,
So this is all semi-simple, right? Semi-simple.
G, yeah, sim-simple, always sim-simple. Sorry. I'm assuming it's sim-simple. So, the usual prototype again is look at SLN and take diagonal matrices in SLN, that will be T for you, and that's a split torus, and it acts on upper triangular matrix, on the Lie algebra of upper triangular matrices, it acts by inner conjugation, adjoint representation, and the upper triangular matrices break up into eigenspaces. Each Eij will be an eigenvector, Eij with Ij on top, and similarly Eij, Ij below, they will both be, there will be eigenvectors. And the Lie algebra spanned by the Eij, I less than j will give you the upper triangular matrices. The group will be the upper triangular group, similarly lower triangular group. So U plus U minus are like this. And next I'm going to define, also going to say that, yeah, I'm going to define a number of other groups now. Firstly, our statement, the earlier statement that there are only finitely many conjugacy classes tells us the following. There exists G1, G2. Sorry? Here. That is Lie algebra. This is u minus, just as this was u plus u. I mean that was called u. This I call u minus, and u minus is the corresponding group. Capital U minus is the corresponding group. This is the Lie algebra. That's the group. Okay. My God, I'm taking a long time. Okay. G is conjugate. There exists a finite set psi in GQ such that every maximal unipotent Q group is conjugate to psi of u plus for some psi in psi under gamma. Gamma is not, I'm not I didn't put down gamma. Gamma is an arithmetic group. This psi will depend on gamma. Psi equal to psi gamma, gamma the arithmetic subgroup. We've seen that there are finitely many gamma conjugacy classes, so that means there are only finitely many. This statement has already been proved, so to speak, proved in quotes because I've left a gap there. So anyway, so finitely many. Now,
So this conjugacy class is under
gamma
under gamma. So
under gamma. There are only finitely many conjugacy classes under gamma, which are for the unipotent groups under GQ there is only one conjugacy class, but under gamma there are only finitely many.
this is what you are right.
That's some statement I more or less proved. Okay. Now, to get this the Borel theorem to complete it, I have to say some more notation. Unfortunately, for I denote by A the set of the identity connected component of TR. This can be characterized as set elements T in TR such that alpha T is greater than 0 for every alpha. This every called phi for every phi. Phi is this correction. Maybe these phi are called K roots. They are called K roots or Q roots. So what for every Q root? When I say, notice that minus phi I have written additively. So on the torus it's taking inverses. So if for the positive phi t is greater than 0, for the negative phi also phi t will be greater than 0. Phi t will be inverse of the other thing. So t in TR phi t greater than 0 for every Q root. This is A. This so for isomorphic to R cross L times, where L is the dimension. That's what A is. And for right. Huh? G in T. Sorry. Yeah, it's R, not R plus. Yeah, right. R plus. That's important. R plus. And now I set AT to be set of G in T with the condition alpha G. T is real number greater than 0. I write AT to be G in T alpha G greater than, alpha G less than, that is AT. Remember, when the Minkowski theorem, this is exactly what we were doing. Took diagonal matrices and every successive quotient it's less than T. AI by AI plus 1 is less than T, which will also give some other constant AI by AJ. When J is greater than I, it will give some other constant depend. You can replace the constant by something else. So for all roots, I took it only for some special roots. Here I am taking it all for all positive roots, as they call it. Alpha g for every alpha greater than 0. Phi, okay. For every phi greater than 0. That is AT for me. Fix K a maximal compact subgroup of G. With this notation, sorry I am loading you with a lot of notation and a lot of unproved statements. And let me also write you have this n plus, which is, and with the algebra n plus, let me write n plus for c greater than 0. N plus c will be the set of elements exponential x in n plus norm x. I introduce some norm, no matter what, some norm on the Lie algebra and write it like this. So this is some compact subset of n plus, because the exponential map is an isomorphism. It's a compact subset of n. Then there exists t greater than 0 and c greater than 0, such that k psi at psi n plus c union psi in psi gamma times gamma is all of Gr. This is the exact analog of the Minkowski theorem for SLN. Instead of SLN, I am replacing G. The upper triangular matrix is replaced by U plus, and lower triangular matrices, diagonal matrices with positive entries is replaced by A. And then I have NC plus this kinds of sets, NC plus and the set AT and K psi AT psi. In the case of GLN, we just had one element. Psi gamma turned out to be one element, but there we also took the group to be precisely SL and Z. If we had gamma to replaced by SL and Z, which is a very specific group. Here I am taking an arbitrary arithmetic group, and if I take a subgroup of finite index SL and Z, that will be an arithmetic group in SL and R, and there you obviously have to add. You can't have not any two unipotent groups are conjugate by an integral element, so you'll have to allow for some finite number of conjugacy classes. When you take gamma to be an arbitrary arithmetic group, even in SL and R. Here we are working with the G and arbitrary arithmetic group, and we know there is this set psi gamma such that every unipotent group defined over Q is conjugate to a standard unipotent group by some element. Any two unipotent groups are conjugates under GQ, but if you want under gamma, you will have to take not just one unipotent group, but some fixed unipotent group plus some conjugates by a finite number. This is the theorem of Borel. And exactly as you prove that the quotient has finite measure in the case of SLN, here also you can prove the quotient has finite measure, because this turns out each of these sets has finite measure.
This is Borel.
No, this is Borel. Borel Harishchandra only said the quotient has finite measure. This is a stronger statement, implies Borel Harishchandra, but this was proved by Borel much later. He gives a proof in his book on arithmetic using the fact there are only finitely many conjugacy classes. I'll see if I can give you a proof. I'm not sure I will, but as I said, it's proved in Borel's book. I will give you a proof provided I can find a pleasanter and simpler proof than what is in Borel's book. This I'll think over this coming week. Next week we'll assume.